We're now going to talk about correlation and marginalization in continuous dimensions. Let's extend our exploration of joint probability distributions. Take the x and y position of Astrocat floating around randomly. In this case, we could think of them as two Gaussian distributions in x and y. If there's covariation, that is, some movements in x are most likely to be also movements in y, we call this a correlated pair of Gaussians. And in this case, you can see they're positively correlated. That is, movements in x that are positive are likely to be related to movements in y that are positive. Covariance of two Gaussians is just defined in the same way as it is for other random variables. It's the expectation of the random variable minus its mean times the expectation of the other random variable times its mean. So in this case, the covariance of x and y will be the expectation of x minus the mean of x and y minus the mean of y. The correlation is simply the normalized covariance. So we take the covariance and we divide it by the product of each Gaussian's individual standard deviation. We know the marginal distributions as well. Just like in the binary case, we're going to average. The marginals are going to be Gaussians. But what if we have a measurement from one of the distributions? The likelihood, the conditional probability of the other will reflect the shared information. So plotted on the right, you can see x and y, that's the same correlated bivariate Gaussian distribution. The marginal of x is a Gaussian and the marginal of y is a Gaussian. But the probability of x conditioned on y with a specific y is not the same as the marginal. We gain information from y about x. First, you're going to explore the basic properties of correlated Gaussians using this widget. And then you're going to explore, using this widget, how information can be transferred from a measurement on one variable to another if there's a correlation.